Alrighty, so next unit, gravitational fields, which, to be perfectly honest, is really not a whole lot different than kinematics and dynamics mushed together, turned sideways, up and down, vertical. Okay? So a lot of the stuff that we've done is sort of going to be repeated, just sort of more in a vertical standpoint. So those of you that are still, I'm trying to kill a little bit of time here, so that those people that are on their phones can finish up conversations and all that, because I'd like to begin. Okay, so here we go. So students will define the gravitational force constant G as a force per unit mass in newtons per kilogram. I read that as students will write the unit newtons per kilogram when they need to. That's how I interpret that. So you should do that. And the weight Fg is mg. The acceleration due to gravity is derived from Newton's laws and determined in the laboratory. We will drop things and determine gravity. Students will describe the normal force in terms of the mutual attraction of masses, then draw simple free body diagrams. The student will be able to define the gravitational field qualitatively. Qualitatively means in words. So you should know that it is a region of space around a mass or another point mass experiencing the force. You should be able to diagram the Earth's gravitational force using lines of force. That's pretty straightforward. Define the gravitational field quantitatively as a force per unit mass. Compare and contrast the terms mass and weight. In other words, know the difference. Describe qualitatively and quantitatively, both with words and numbers, apparent weight changes in vertically accelerating systems like elevators. You will derive the acceleration due to gravity from free fall and Newton's laws. You will perform an experiment to calculate G near the surface of the Earth, which will be like here in Dauphin in our classroom. Solve free fall problems. Describe terminal velocity both qualitatively and quantitatively. Define the coefficient of friction, funny looking symbol, as the ratio of the force of friction and normal force. Distinguish between static and kinetic friction. It seems like a lot, doesn't it? Compare the effects of the normal force, materials involved, surface area, and speed of the force of friction, and solve problems with the coefficient of friction for objects on a horizontal surface. So there are only sort of two solved problems, that one there and this one here, okay? But a lot of them are kind of theory. They are certainly. Some of them I can cover like in a single day.
What is funny looking symbol?
What is funny looking symbol? The Greek letter M, pronounced mu, although I'm told that the proper pronunciation in Greek is me. But every scientist that I've ever met has called it mu. So, don't know. And I don't know what the kids in Greece use for that symbol. I've always wanted to know that. Mu. It's a U, Cole, with sort of a tail on front, yeah. Most students just write U.
What is that?
It's the coefficient of friction. It's a measure of how rough two surfaces are, how much friction there is.
Okay.
Okay? All right, so that's about all I have to say about that. Let's do a clicker quiz. Where is it? All right, well, let's just see how we did here. So, there is no gravity in a vacuum? False? False? What holds the moon in orbit around the Earth? Gravity.
I thought we were
Didn't the astronauts weren't they attached to the Earth, to the moon, like they were attracted to the moon, right? Right. Those of you with earbuds, get them out, you guys. Junior, get it out so you can hear.
I got that one right.
NASA has built a zero gravity chamber. Well, it's a bit of a misnomer. It's false. What do they have? They have big giant pools, right, where they practice in. Not really zero gravity. They use buoyancy to sort of simulate. They also have the Vomit Comet, which is a plane that does this, and you can float in. $5,000, you can go to yourself if you want. And do it. $5,000 US. It is. It'd be a lot of fun.
No.
I'd like to try it, but I'd wear a helmet.
Can we pool some money together?
Maybe a field trip. Can you imagine the paperwork I'd have to do to take you guys on a zero gravity?
And how much we have to pay? No, it's not.
Gravity is the same as air pressure. False. That's good. Looks like very few people put true.
Which one is this?
Number 3. Number 4, gravity pushes down. Cole got me. Because it pulls you down.
Oh. I actually did.
I try not to let gravity get me down. Some days it works better than others. Thanks, Brett. Gravity is the same as magnetism? False? Really? A bunch of people said true? Gravity in space is 0. Is this not the same as the first question? False. Look at how many people said true. No, not true. What do you think is holding Jupiter in orbit around the sun?
Gravity.
Gravity.
Yeah, because you're object.
Okay, this one always scares me.
Gravity's just a theory.
During a full moon. Okay, first of all, do you know what a full moon is, Cole? A full moon is like when you see the whole moon, right? The moon has a higher gravitational pull, creating a higher tide. And I'm going to guess, yep, not surprised.
The moon's always the same size.
You realize that when the moon is like a half moon like this, it's still all there. It doesn't disappear. You just can't see it. It's like, see the ball?
It evaporates.
Where'd it go? You just can't see it, you guys.
It's gone.
Oh, science education. What weighs more now? Please, I'm begging you.
Oh my lord.
Who got A?
Someone I think is playing games.
You get A? I didn't get it. I got C.
Black holes don't suck everything into them.
I put the ball.
No, that's true. Because if it was false, guess what? We'd be in a black hole.
There it is.
How do you know we're not?
Well, true enough. Although our
We're in a
density
black
is...
hole within a black hole within a black hole.
No. Here's how black holes work. I'll give you the quick version of
Oh,
Bro, you know, we
I
could
got
do that.
that thing wrong.
it. If you've got a star, Johnny, if you've got a star that becomes a black hole, right? So you've got planets and other things orbiting said star, and when the star becomes a black hole, it gets much, much larger, and then gravity takes over and it sucks it back in, and basically the star gets squished down like this to a point that is incomprehensible of density. Okay? The only things that get sucked into it are things that would have been sucked into the star before. Anything that's orbiting it is still orbiting it. That's how we know there's a black hole, because we have a planet or whatever orbiting nothing.
Well, something.
Something. Well, but you can't see it. It's still a star, right? So that's what a black hole is. It's simply a star that has been stretched right down. Clearly, this is way more important.
The biggest star in the galaxy.
If I get time, Brett. I got lots of videos to show you today. Okay, number 10. Which of the following diagrams most closely represents the gravitational forces that the Earth and the Moon exert on each other? Note that the mass of the Earth is about 80 times that of the Moon. Okay, so there's my model of Earth. Here's my model of the Moon, not to scale. That's actually 80 times bigger than this. Okay, which one is most closely represents the gravitational forces? So is Earth, Moon like this with a big giant pull? Or I guess that's a big giant push, isn't it? Yeah. Oh no, I guess what that is, that's the pull on Earth from the Moon, right? And that's the pull on the Moon from the Earth, right?
Makes sense.
Well, regardless, the answer is C. Now, why is it C? What's different about C, Jordan? In C, the forces are equal. Exactly. There's the Earth. Here's the Moon. Between objects, for every action, There is a equal and opposite reaction. Equal. How come the moon isn't, or sorry, the Earth isn't attracted to the moon? Because it's bigger, it has a lower acceleration. What effect do we have on Earth from the moon? And we already talked about it today. Water. The tides. Right? The water is pulled to this side as the Earth turns around, and then as it goes around, then the other side of the water. And that's why the tides go up and down, because of the moon's gravitational pull. Okay? Now, just as a sort of an afterthought here, if that is the Earth, how close should I put? I'm going to give you, I need 3 volunteers.
Yeah.
Right here.
Hey.
Oh, I'm coming up to you. Yeah.
Okay, these guys all have a copy of the moon. If that's the Earth, I want you to put your moon, how far away do you think it is to scale of the Earth there? Like your moon is pretty close.
And this is the sun.
No, that's not it. So I want you to stand, holding your moon where you think the moon should be. How far away?
Ty's gone.
Leaves the school.
Leaves the school.
Drives the little behind you.
No, drive.
There's no difference really. Well, a little bit, I guess. Okay, how many people think Junior's right?
I'm not sure.
Scale, they're still wrong. All right.
How many people think Cole is right?
I'm not sure.
How many people think Ty's?
Sure.
Let me just see how far out he is. Far out, man.
Where is he? He's driving away. He's gone. Okay.
Well, he's gone.
He's orbiting.
But I'll tell you what, these guys are nowhere close.
Is Ty close?
Ty's a lot closer.
Ty's orbiting right now.
Yeah, it's at least 30 meters away.
Yeah, he is. He is one guy.
Did he? Thanks, so.
He's orbiting.
Yeah,
He's orbiting.
And he's keeping Phoenix for orbiting.
Okay, is that the last question?
Yeah.
Oh well, we'll get him out. Okay, so I'm going to explain a little bit about gravity today. Unfortunately, today is going to be one of those days for me a whole lot. Okay, I suggest follow along on here.
We have to write it.
No, highlight, make a note or two in the margin, that kind of thing. Okay? All right, so it says free fall explained. Galileo showed. Brandon, can I start? Do you realize I'm starting? Galileo showed that falling objects accelerate equally regardless of their masses. Now, this is strictly true if air resistance is negligible. Do you know what the word negligible means? It means really small, so small that you can basically ignore it. It's kind of like leaving a penny on the counter. Not worth the bother. If air resistance is negligible, that is if the objects are in free fall. It is approximately true when air resistance is very small compared with the mass of falling object. For example, a 10-kilogram cannonball and a 1-kilogram stone dropped from an elevated position at the same time will fall together and strike the ground at practically the same time. This experiment, said to be done by Galileo from the Leaning Tower of Pisa, demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. So Aristotle, you probably heard about him, Greek guy, right? He said that an object that's 10 times heavier should fall 10 times faster.
No.
2,000 years and no one bothers to actually try it. Hard to believe. In fact, my guess would be people tried it, said Aristotle, you're wrong, and perhaps he had him thrown in jail or killed. Who knows? Hard to believe that for 2,000 years no one actually checked it out. Right? But anyways, Galileo did do it. Rumor has it from the Leaning Tower of Pisa. Have you? Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerations were equal. The explanation is the straightforward application of Newton's second law, and is the topic of the cartoon Backyard Physics, which I'll get to momentarily. But first, maybe you don't believe me that this is true. So, my good friend Jake Rampton made a little video for me. Here it is.
So right there on the side, so we got
Flip over your page to this cartoon. Now, when they say cartoon, it's not a funny cartoon. Sorry to say. Okay? So, you've got two kids sitting outside an apartment, and you've got a woman inside, and she says, if I drop the bag of clothespins and the single pin at the same time, which will fall to the ground first? The one kid says, that's easy. The bag of clothespins is heavier, which means gravity pulls on it with more force. Is that true? That is true. It is more force. How come? Because it's bigger. The bigger you are, the more force. That part is true. So the bag of pins,
The harder you fall, isn't it? What you're saying.
the bigger you are, the greater gravitational pull there is on you.
That makes sense.
Yeah, but that's not the same.
You're right, it's not the same. So the bag of pins will accelerate more and hit the ground first. And the other kid scratches his head and says, physics, physics, physics. Maybe he says, Bennett, 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 I don't know. He says, not true, the bag of clothespins has more mass, which is to say it has more inertia. Is that true? Inertia is the tendency of an object to keep on doing what it's doing. It's like the tablecloth trick, right? Is that true? It will be less responsive to gravity and lag behind the single pin. So he says the single pin will hit the ground first. And you just saw it in video two different ways. Sorry, gang, tie score. How come? And this is the part that you have to know. Since the bag has both a greater weight and a greater inertia, one offsets the other. The weight, big weight divided by big mass, is the same ratio, the same fraction as small weight, small mass. The same acceleration. And I'm going to explain that with a diagram right here. If you've got, let's do this. If you've got F equals ma, okay. If you've got a larger m, right? You've got a larger m. What's the acceleration due to gravity on Earth? It's 9.8. The acceleration is the same. So if you've got a really big mass, then you've got to have a really big force. Okay? But the acceleration, A equals, this is an A equals F over m is true for big objects because they have big forces. They also have big masses. That's why they have big forces, because they have big masses, right? So the ratio of F to m for big and small are the same. Okay? And that's basically what it says in the rest of that paragraph right there. Okay, and I'm going to read this version of it. I've sort of explained it in Bennett version. I'm going to read it in Dr. Hewitt's version here. So go to the second paragraph where it says, recall that mass, quantity of matter, and weight, the force due to gravity, are proportional. A 2 kilogram bag of nails weighs twice as much as a 1 kilogram bag of nails. So a 10 kilogram cannonball experiences 10 times as much gravitational force or weight as a 1 kilogram stone. The followers of Aristotle believed that the cannonball should accelerate at a rate 10 times that of the stone because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little more thought will show that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass. In symbolic notation, there's that F over m thing, where F stands for the force and m stands for the corresponding large mass. The small f and m stand for the smaller weight and smaller mass of the stone. We see that the ratio of weight to mass is the same for these or any other objects. All freely falling objects undergo the same acceleration, same place on Earth. In chapter 2, we introduce the symbol G for acceleration. So the letter G on Earth stands for gravity, which is equal to, there's the number right there, you can highlight it if you want. What's G on Earth? Negative 9.8. Negative 9.8 newtons per kilogram, or if you prefer, minus 9.8 meters per second squared. Okay? In the famous coin and feather in a vacuum tube demonstration discussed in chapter 2, the reason for equal accelerations was not discussed. Now we know that both freely falling objects fall with the same acceleration because the net force on each object is only its weight. And the ratio of weight to mass is the same for both. So if you were to drop a feather and a coin here on Earth, how would they fall? Okay, Junior, Me, I'm teaching. Okay, I don't have a feather and a coin, but I got a tennis ball and a piece of paper.
The tennis ball's gonna hit the ground.
Tennis ball's gonna hit the ground first, but we just showed that
It's like
lots of surface area, right? Exactly. Lots of surface area. Golf ball,
yeah.
but
Is that my parachute cord?
let's just do it without clicking, shall we? There's no need. If you were on the moon, dropped a hammer and a feather from the same elevation at the same time, would they strike the surface of the moon at the same instant? Yes, they would? How many people say yes on the moon? Really? Wow, that many people. How many people say no? Just Olivia. Okay. You sure? Oh, you're dropping a hammer and a feather on the moon. Now, unfortunately, I don't have a magic school bus, and that's too much paperwork anyways, but through the magic of video, would they strike at the surface at the same instant? The answer is yes, they would. Now, what is the acceleration? Did you notice that they actually fell a little bit slower? You know why? Gravity on the moon is only 1.6. Okay, flip the page over. I gotta keep my pace going here. Or it says 5.7. I'm following you there. Okay. The feather and the coin fall with equal accelerations in a vacuum, but quite unequally in the presence of air. When air is let into the glass tube and is again inverted and held upright, the coin falls quickly while the feather flutters to the bottom. Air resistance diminishes the net forces acting on the objects. The net force decreases a tiny bit for the coin and a whole lot for the feather. The downward acceleration for the feather is very brief because the air resistance builds up quickly and counteracts its tiny weight. The feather does not have to fall very long or very fast for this to happen. When the air resistance on the feather equals the weight of the feather, the net force is zero. And what happens when the net force is zero? It hovers, stops accelerating, right? So the same thing with the piece of paper. Because of the large surface area, air resistance very quickly will balance. Here's my sheet of paper. And when the gravitational force down is equal to the air resistance up, what happens? Stops accelerating, and it falls at that speed, which is very little because it hasn't accelerated for very long. Something heavier like a tennis ball will take a lot longer to reach that speed. What is that speed called? Anyone know? Terminal velocity.
So if you drop it from high enough, will different things will fall high enough?
It depends on their shape. Like if Jake had dropped this compared to something, say, like a volleyball, this would have hit the ground first. Okay? Because the volleyball, maybe not from the height of a silo, but if you go high enough, a volleyball will reach terminal velocity before something like this does. So yes. Okay? So, I'm reading the second paragraph there. Acceleration terminates. The feather has reached its terminal speed or terminal velocity. You should know what that word means. It's bolded. You should highlight it. Terminal speed or terminal velocity is the fastest thing that fastest speed that an object can fall at, and it's reached when the air resistance is equal to the force of gravity. We've reached terminal velocity. Air resistance does not have as much effect on the coin. At slow speeds, the force of air resistance is very small compared with the weight of the coin, and its acceleration is only slightly less than the acceleration of free fall, g. The coin might have to fall for several seconds before its speed is great enough for air resistance to equal and cancel its weight. Its speed at this point, perhaps as much as 200 kilometers an hour, would no longer increase. The coin reaches its terminal speed. Now, if you were to jump out of a plane, the terminal speed for a skydiver varies from about 150 to 200 kilometers per hour, depending on the weight and orientation of the body. A heavier person will attain a greater terminal speed than a lighter person. The greater weight is more effective in plowing through the air. Body orientation also makes a difference. More air is encountered when the body is spread out and its surface area is increased, like that of the flying squirrel in Figure 512. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel, while the light person falls head or feet first. A parachute greatly increases air resistance and cuts the terminal speed down to 15 to 25 kilometers an hour, slow enough for a safe landing. So when you jump out of a plane, You fall faster, faster, and faster. You reach a terminal speed of, say, 200 kilometers an hour. You pull your parachute. What happens? You slow down. Now, you always see when a skydiver falls, what do you see? The person with the parachute does what? Kind of goes up. Do they actually go up?
No, it's just they slow down.
Okay, Zane, you should be listening to me. But you're not. You've clearly got your phone out and you're paying attention to someone else. It's pretty obvious. Hydro's not going to let you have a phone at the top of the pole. They won't. When the skydiver is falling like this with the counter person and this person pulls the chute, what does the counter person do? It keeps falling. And so it's all about that frame of reference, right? It looks like this one is going up, but really you're just slowing down. And then when you hit the ground, you reach a new terminal velocity of about 15 kilometers an hour, which is safe to land it, to not break your leg, exactly. Yeah, if you don't bend your knees, right? Exactly. Oh yeah, where am I? If you hold, last paragraph there, if you hold a baseball and a tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. But if you drop them from the top of the building, you will notice the heavier baseball will strike the ground first. This is due to the buildup of air resistance at higher speeds, like the parachute in question. At low speeds, air resistance is often negligible, but at high speeds it can make quite a difference. You're driving down Main Street, you stick your hand out the window, you do this. That's always fun, right? You just stick your hand out going down Main Street, what does it feel like?
It's a lot of wind.
Just like 50 kilometers an hour down Main Street, not too bad. But you do that going down the highway and you might tear a rotator cuff. How come? Greater air resistance, right? Your hand is the same size, right? You're going faster, it's a greater force. At low speeds, air resistance is often negligible, but at high speeds it can make quite a difference. The effect of air resistance is more pronounced on a lighter tennis ball than on the heavier baseball. So the acceleration of fall is less for the tennis ball. The tennis ball behaves more like a parachute than the baseball does. When Galileo reportedly dropped the objects of different weights from the Leaning Tower of Pisa, the heavier object did get to the ground first. That did happen. However, the time distance was only a split second, rather than the pronounced time difference expected by the followers or herself. He purposely did 10 times heavier than one, because it would be obvious if they landed 10 times faster, right? When Jake Rampton dropped those two things, it was 4 times. From a significant height, you wouldn't want to be jumping off the silo, right? How tall is a silo?
Tall.
Maybe 70 feet?
It's noticeable in slow-mo that the judge is a little bit.
Really?
But it's also taller, so.
That's true. And he may not have actually dropped them at exactly the same time, right? Yeah, that's true. In fact, the one that Charles did in class, I was surprised it actually worked as well as it did. If you look at it close, you can actually see the rod actually kicks first, but I think it's because of the angle that I was, like my camera was up like this, I probably should have been down lower. Okay, so good enough there. So there's a couple questions here. If a heavy person and a light person open their parachutes together at the same altitude and each wears the same size parachute, who will reach the ground first? Heavy person, light person, same time, impossible to tell. You're going to go into an airport? Oh.
Redoing the clicker thing?
There's only a couple questions. I forgot to. Most people put them away, I think, right? Which one is it? I don't want to make sure I get time for videos here, too. Which one is it? The answer, is it on your page? It's not. The answer is the heavier person will reach the ground first. Like a feather, the light person reaches terminal velocity sooner, while the heavy person continues to accelerate until a greater terminal speed is reached because of their weight.
What heavy person's like?
They'd have to be in the same orientation. The heavy person moves ahead of the light person, and the separation continues to increase as they descend. So while it is theoretically true, in real life, friction actually plays a significant amount, depending again on how high up you go. Last question. If the force of air resistance is the same for a falling baseball and a falling tennis ball, which will have the greater acceleration?
Baseball.
Don't say the same. It's true the air resistance may be the same for each, but that doesn't mean the net force is the same for each, or that the ratio of net force to mass is the same for each. The heavier baseball has a greater net force. You guys should be listening. I'm explaining. The heavier baseball has the greater net force and greater net force per mass, just as the heavier parachute as previously considered. And so on. Okay.